So good afternoon, everyone. Very welcome to this webinar. We are waiting for some more couple of minutes to allow all people entering the webinar. I see that there are still people entering now. The number of participants is increasing. I'm very happy also to see that there are many people coming. It means that such a topic is a topic of interest. We have already here all the speakers. Welcome, Aval Sadek. Welcome to everyone. And I believe that now we can start. So good afternoon, good morning, good evening to everyone, depending where you are located. And very welcome to this webinar. This is the webinar of the working group related to the ISPRS working group related to, let us summarize saying, to citizen science. And I'm very pleased to be here with my colleagues, Professor Sidalia Ponte and Professor Xiaoguang Zhu. We are the three co-chairs of the working group. And with respect to this initiative, the initiative of the webinars, when we were asked, we were very happy of proposing something that we believe is very relevant today in the world of citizen science, which is how we can use artificial intelligence or machine learning, deep learning, and so on, for improving citizen science, and vice versa, how the data coming from the citizen science can be used together with artificial intelligence for improving our knowledge about the world around us. So very welcome. And before starting, I want immediately, in such a way not to forget, to thank the organizers, so the students of the ISPRS Consortium, for providing the technical help in the organization of such kind of initiatives. Wonderful. So today we are going to speak about machine learning and citizen science, and specifically the webinar is organized in this way. Before we have three short presentations by four speakers, and then after that there is a part related to question and answers. If you have questions, please write them in the chat or in the question and answer part in such a way that we can collect them and then reuse in the second part of the webinar during the discussion. With respect to our speakers today, we have, as I said, three presentations. The first one will be provided by Sven Schade, the second one by Mariam Latvian and Jens Ingelsand, and the third one by Christopher Beto. But let us consider all one at a time. So we will start with the presentation of Sven Schade. And I want to briefly introduce Sven to you. Sven is a geospatial information scientist by training, with the research interests covering digital governance, multidisciplinary interoperability, and public participation in science for policy, always with a view to improve inclusive and sustainable transitions. He works at the Digital Economy Unit of the European Commission's in-house Scientific and Knowledge Management Service, the Joint Research Center, which is known also as JRC. Here, he leads the research on digital transformation and the modernization of the public sector for recovery. Sven has co-authored more than 100 publications in the fields of geospatial semantics, citizen science, and next-generation knowledge infrastructures. So, fantastic. We are very happy to have you here, Sven. And then I give you the floor for 10 minutes for presenting your topic.
Excellent. Thanks a lot, Maria. I hope you see also my camera in a second, and now also my slides. Is this fine?
Yes, fine.
Excellent. So hello, everyone. And indeed, I'm also very happy to speak to you today about the combination of human intelligence and machine-based reasoning. And many thanks for the kind invitation to present some of our work today. I'm Sven. As Maria said, I'm working for the Joint Research Center of the European Commission. And the last 5 to 6 years, we really did a deep dive into citizen science. And you will see some of the results in the next 10 minutes. Of course, what I'm showing you is not only the result of my own work, it's also done with a lot of dedicated work from our entire team, and especially Fabiano and Irena, who are the two main people behind our software development efforts, and they also are joining here today. So what I want to talk about in the next 10 minutes is really to walk you through a little bit of our past work, starting from what we did in the world of mobile applications, so a very prominent topic in citizen science. Then I will speak very briefly about some experience we have on automated image recognition. And then I will move to the use of social media, here in particular, looking into chatbots on Facebook. And based on these three different experiences, I will give a rough indication where we see this work going in the future. So let's indeed start with a classical example. Already 6 years ago, we started developing a mobile phone application to support citizen scientists in recording information about species, about plants and animals in this case. And we did it, of course, in an open way. So we published everything on the app stores, but we also published the data and the entire source code with an open license. And we really did this work with the European Union in mind. So we are really supporting so far 13 different languages, and we keep adding different languages to the app. And we also implemented what we call a roaming functionality, so that depending on where you are, we are partnering with different institutions, and you can report species which are important for different regions within the European Union. So this is basically our flagship application on species which are especially alien, so not in their natural habitat, and are threatening local biodiversity and human health, agricultural production, and so on. So this is really a big experience we collected in developing such an application, but also to manage the data flows from citizen scientists, integrating this with validation mechanisms, and ultimately integrating the data in a scientific database that is also used for policy implementation and monitoring at the level of the European Union. So this was basically our first way to get our hands dirty to support citizen science and connect it to policy of the EU. And what we really found over the past 6 years is that there are many apps. There was a whole peak of everybody developing an own app, but only some survived over time. for different technical reasons and organizational ones. But we also saw that apps alone are not the solution to engage citizens in a wide sense. And we also believe that we pretty much reached the limits on developing an app to support citizen science. And we really put as many functionalities in there as they can be digested. And also we found that actually interconnecting data from these apps with official data flows is totally possible. So this is really where we came from in the development of apps, which has been really a hype like 5 years ago. And now we really see things stabilize. To add one more ingredient, when we think about people submitting with a mobile phone images, we may also think of actually automatically recognizing which kind of images are sent to us. So is there actually a plant or an animal on the picture, and which kind of species is it, and is it really interesting for us? So in order to get a sense of the capabilities of automated image recognition models, we tested a few of them. Especially successful was a model which was developed by iNaturalist in 2018 to really recognize a rich set of species. And we were using all the pictures we were collecting by our app to identify if the off-the-shelf model can actually help us identifying these species. You see in this graphic that actually in 1/3 of the cases, an off-the-shelf model was successful. In many cases, it was not. And this has, of course, a lot of different reasons, depending how the model was trained, depending on the quality of the image, and additional factors. So from this initial experience, we are currently collaborating with the University of Münster, the Institute for Geoinformatics, to now actually do a review of which kind of image recognition models are out there to recognize species, and to test which of those may suit our needs best. So that's currently an investigation that is ongoing to really understand the possibilities, but also the limitations of using automated species recognition. Again, we have a few main findings from this activity. Most likely, if you're interested in certain animals and plants, there will not be the one model already available, and you may need some additional training and tuning for a selected set of species. Image recognition is as good as the images which are provided. So we are also looking towards guiding people to take images which are easy to analyze, and eventually also to take more than one image. So after you picture a plant, maybe you also take a detailed picture of the leaf. We see also that some species are easier to recognize as others. For example, fast-running animals are extremely difficult to picture in the first place. And then we still see a need in the world of automated image recognition that a lot of models, but also data sets for testing and training can be shared better. So we really see a need there for further improvement in the sphere of open up science. Then, to come to the third ingredients we're looking at, we actually thought, okay, wait a minute, we always have to update these mobile phone applications to the latest operating systems. Can we actually replicate the exact functionality we have in our app on social media platform? So what Fabiano and Irena primarily implemented was a chatbot that is able to provide similar functionality to allow people to look into different species out there, to report a sighting, and to get their observations validated. So we did this example implementation on Facebook, and it's still at an experimental stage, but we also investigated this side of the technology stack. Again, early lessons are that these chatbots differ from platform to platform. So using Twitter, Instagram, and Facebook all follow different rules. Also here, as on mobile phone apps, you of course depend on these platforms if you use them to manage dialogues. But we also see that using different social media platforms, it's an interesting tool to reach additional and new audiences to engage with. And we also see that we can replicate interactions we know from before, but maybe we can do a bit better. So actually, what I want to close with is really moving towards our vision, what we want to do. So taking the experience from the mobile app, from the automated image recognition, and from the chatbot, we really now want to work towards the best combination of human reasoning and machine intelligence. And we call this collective intelligence. So we really want to have a people-centric use of technologies and also explaining the artificial intelligence we use behind the scenes. So the idea really is to combine chatbots, automated image recognition, and some translations between these two worlds. To just put this in a very simple dialogue flow, you may imagine that you actually start an interaction with a chatbot by just dumping an image into the dialog box. We run this image towards an image recognition model and say, oh wow, on this image I see one animal and two plants. What do you want to know more about one or the other? Okay, one of the plants you want to know more, fantastic. Can you also actually give me a picture of a leaf? And with this information, we interact with yet another model to identify which kind of species it is. And if it should happen to be a species which is invasive in Europe, then we could say, oh, wow, this is an important observation you made. Would you like to share this observation with the team at the JRC? So this is a little bit the new interaction we envisage between humans and machines facilitated by chatbots. And you can easily imagine that this can be generalized. So you can actually go through the same workflow, but at the end, you don't find an invasive species, but you find a red list species, an endangered species. So again, we could say, wow, this is an endangered species. Would you like to report it, for example, to the European Environment Agency? And we open just a different dialogue flow. And you can imagine a lot of other application areas for other kinds of species that other organizations might be interested in. And here really the sky is the limit. With this, I really did a bit of a dump of the different technologies we were investigating over the past 6 years. I explained a bit the lessons we learned, but also gave a bit of a direction into the future. And I hope this inspires some thoughts and interesting questions. I stop here. Thank you very much for listening.
Thank you to you, Sven. It's always a pleasure to listen to your presentation because really you are doing a lot of things in the area of research at the European Commission. And I believe that your vision is always so important for us. So now switching, because we don't have time now for the question and answer, they will be made after. Now we go toward the second presentation. The second presentation will be a presentation by Mariam Latvian and Jens Ingesand. So before I want to shortly introduce these two speakers, Mariam obtained her Bachelor in Geomatics Engineering from Tehran University. Then she received the Masters of Science in Environmental and Geomatic Engineering from Politecnico di Milano, with a thesis on urban climate classification using satellite imagery. Then in collaboration with the University of Applied Science and Arts, Western Switzerland, she began her PhD at the Politecnico di Milano Department of Civil and Environmental Engineering in October 2017. And her research focuses on challenges in citizen science projects, including participants, motivation, and data quality. She works on developing machine learning algorithms for automated data validation in citizen science projects. So this is the presentation of Mariam, and Jens is a professor in geoinformatics and GIS at the University of Applied Sciences of Western Switzerland within the Institute of Spatial Engineering and attached to the research group Geomatics. After his training in computer science and geography at the Polytechnic University of Chalmers in Sweden and the University of Gothenburg, Sweden again, and his PhD at the EPFL in Switzerland, he worked in various functions in the private sector and for the cantonal administration, so the local administration. His interests are web mapping and mobile applications, citizen science and VGI, spatial databases, geodata infrastructures, augmented reality, and human-computer interaction. So wonderful. We see that also in this case, we are very high-level speakers. So I give immediately the word to you two.
Thank you. I hope everybody can hear us. We will share our screen.
We can.
Yes, thank you. Okay, can you see our screen?
Yes.
Yes, great. Thank you. Hi, everybody. Thank you very much, Maria, for this introduction. I will talk first, and then I will pass on to Mariam. So today we will present our different aspects in the field of the combination of machine learning and citizen science, and especially about data validation, and we will also talk about sustaining participation. So we can state today that there's an availability of large amounts of citizens' data around, and there are different ways of using these different data sets to address challenges in citizen science projects, in existing ones and also in new ones. In citizen science, if we simply compare these two fields, on the one hand we have citizen science, where of course it is very important to have participants. Without participants, citizen science doesn't work. So we need to keep the participants motivated in order to continue collecting data, interpreting data, and so on. But on the other hand, we also have challenges regarding data quality. So that the data that is collected by the participants is of high quality, so that it can be reutilized afterwards. On the other hand, we have machine learning. Machine learning requires large amounts of training data. So we need to have already labeled data that we can use in order to train an algorithm. And once we have that, we can afterwards use machine learning. So our investigation is really about the combination of these two approaches, where we can see what are the benefits, but also what are the challenges in combining these two approaches. So on the next slide, I will just give some examples where a combination of these two fields can give benefits. So if we start, for instance, on the left about data quality, so we can, once we have data, we can use machine learning in citizen science projects to automatically validate metadata. For instance, the location of species or image data. Sven was presenting also some very interesting approaches in this field, and also automatic data filtering, where we, for instance, can take into account different levels of volunteers, different levels of expertise, and by doing that, validate the data. And we have one field that we think hasn't been investigated very much by the community. It is about engagement and sustaining participation. Many citizen science projects that we have seen, that we have investigated, that we have been involved with, we have seen that at some point the citizen science project starts. There are some people contributing with data observations and so on. But then there's always this problem that you need to keep these volunteers and in order to keep your project running. So we think that there are many different possibilities to use machine learning in order to engage the public and sustain participation. For instance, through automatic recommendation systems based on people's interest, or also real-time feedback generated by machines that can be given to volunteers. Also, what Sven presented towards the end was also very much in this field. Then also about data collection, that we can automatically classify and detect different objects, for instance, based on images. We can also use artificial intelligence to for instance, have cameras or sensors that automatically detect different phenomena. And we can also automatically generate metadata. Maybe on the next slide, I will just also see this as a process that on the one hand we have volunteers. They need to be motivated in order to contribute, so they're contributing with data. Once we have data, this data needs to be validated, and once it has been validated, it's also very important to give a feedback to the users in order to also keep them motivated. So that there's a circle where we can use machine learning at different stages, and by doing that also keep the project, the citizen science project running. I will now hand over to Mariam, who will present some very specific examples how these different fields can be combined.
Thank you. Hi everyone. So to continue what Dr. Ingenson mentioned, especially in the last slide about this process of validation and giving feedback to the participants, we implemented a biodiversity citizen science project to collect biodiversity observations, but in the same time providing real-time feedback to the participants and automatically filtering observations. This process of automatic filtering works as follows: that when a participant contributes an observation to the platform, the observation passes through an automatic filtering, and if it passes successfully, it would be classified as a valid observation, else it would be flagged as unusual. And in this case, the participant will receive a real-time feedback about the observation, given the information that why this observation is flagged as unusual. And the participant would decide either to modify the observation based on the given information and resubmit, or to confirm the observation as it is. And in this case, the expert would perform the final validation. In this case, the main two objectives is, on the one hand, to simplify data validation task by reducing the number of observations that will be passed to the expert to be validated. And on the other hand, we are trying to see if we can, with this approach, we can increase engagement and sustain participation by providing real-time feedback to the participants. And also also providing a learning opportunity for the participants while they are making contribution by providing them with informative feedback. So we applied 3 filters in this application: image filtering, data, and location filtering. But since our study is focused on the location validation, in this presentation we only talk about the location validation. So to perform location validation, we used species distribution modeling in such a way that we used the species observation data along with the environmental variables to feed and train machine learning models, and to get species distribution models as the output, which was then used to validate new observations. And for the species data in this study, we considered for the moment only bird observations. So we obtained the bird observations for Switzerland from 2016 to 2020. And we can see here the bar chart shows the distribution of the observations between different land cover classes. And for the environmental variables, we use land cover, elevation, slope, and NDVI. Using these environmental variables and species observation data, we trained 3 algorithms: naive Bayesian, random forest, and deep neural network. However, for random forest, we trained standard random forest and also balanced random forest. And here we can see that he is an example of a sample data set for one species that is one of the common species called Scorone or carrion crow. that for this species we had 3,200 positive records, meaning that the species was observed in those locations. And for each species, we generated 5,000 artificial absences or pseudo-absences. And for training, we consider five-fold cross-validation, and in order to avoid overfitting, we used special blocks to take into account the spatial autocorrelation among the environmental variables. So the results from the algorithms that we trained, we compared the performance of the different algorithms, and we saw that balanced random forest for most of the species, we trained for 101 species, these 4 algorithms, and we saw that balanced random forest performed better relatively compared to the other 3 algorithms. So we decided to use the models trained on this algorithm to validate the new observations. As an output, we had actually 2 types of output. We had like the one binary classification, so the presence and absence, and another output, which is the probability of occurrence of a species, probability of observing a species in a specific neighborhood, which was what we used in order to validate the new observations. So up to now, we have trained our models, but how did we use this to validate our observations? So apart from our platform that we had to collect the data, we implemented also an API, which it works in such a way that it has the safe trained models, and when a participant contributes an observation, the environmental variables in a neighborhood of 1 kilometer around the location of the participants is extracted in real time, and these environmental variables, along with the species name, is passed to the API, which will be passed to the model. And the model predicts the probability of observing the bird species in that neighborhood of 1 kilometer around the location of the user, and returns the probability of occurrence on the model, and then the machine generates the feedback with the information with this probability plus with the information of where are the possible zones that the observation, the species can be observed. So given this information about the API, we give two types of feedback to the participants. One is that if the probability of observing a species is less than 50%, if it's higher than 50%, we give this feedback only for the information, to give information to the participants. So we give that for your information, this species in a neighborhood of 1 kilometer around your location. This is the probability, and the species can be observed in these locations. And if the probability is less than 50%, we ask the user to make sure to confirm that the observation is added correctly, or the location or the species name. And this observation would be flagged, and the expert would make the final validation. But another point that we added using this API is to give a user-centered suggestion in such a way that, again, in a neighborhood of 1 kilometer around the user location, we give the top 5 possible species that can be observed, with the aim of giving an idea to the user that what are the possible species that the user can look for, but also if the user has observed a species, can check this list to see if the species that observed is within this list or not. We did a testing of this application during the last 3 weeks with some users, and during this 3 weeks period, over 200 users visited the application, 36 people registered, and 14 people contributed. It's interesting that we are all familiar with this long tail of participation, or this dinosaur tail of participation, that we have all seen it in OpenStreetMap projects, VGI projects, other citizen science projects, that usually a few number of people contribute most amounts of data. And it was interesting that we saw the same trend even for trying this application for this short period. Another point, we checked the top 20 bird observations that were collected. So we saw that the first two observations, the first two species are the most common ones. So meaning that users were more collecting the species that they knew the name. But another interesting point for us was that for the user, in order to receive this feedback, they needed to provide the name of the species, the common name of the species in English. And most of our users were French speaking, so they were more familiar with the name of the species in French. But the fact that most of the users were providing the names in English, we can say that it's a hypothesis that they were willing actually to receive this feedback and to receive this information. However, to be sure, we are sending the users a questionnaire to more know their feedback about the application and their opinion about receiving these kinds of feedback. So to wrap up, our idea in this project was to see how we can use existing data from other citizen science projects. In this case, we used eBird to validate new observations in other citizen science projects. And also by combining machine learning and citizen science projects, our aim was to see how we can simplify data validation projects, improve data quality, but in the same time to see how giving this informative feedback to the users can help in sustaining participation and increasing the knowledge of the participants about biodiversity, for instance, here by giving them information about where they can observe some species, what is the probability of observing the species, and so on. Finally, for some future works that we have in mind to add to this project, is that the first one is that for the moment we consider for the validation, we considered location-based data, but we would like also to include temporal data such as the seasonal variation, the weather, and so on, which we would like to include in our models and to validate the data accordingly. Another point is to test this real-time location validation for other organisms besides birds. And a third point that we would like to see how this approach of combining machine learning with citizen science can be integrated in other citizen science projects besides biodiversity, because the main focus nowadays is on biodiversity citizen science projects. When we see machine learning is involved, the main focus is in biodiversity projects, which is very interesting, but we would like to see how this can be also integrated in citizen science projects in other areas. And finally, and according to me, the most important points and maybe the purpose of also this seminar is to investigate more how this combination of artificial intelligence and citizen science can be beneficial for citizen science projects, for citizen scientists. What are the traits, or what are the benefits and risks? For instance, if we are increasing engagement by giving real-time feedback to the participants, is it possible that we are risking also to demotivate participants because of too much automation of the task? If we are improving, let's say, data quality or simplifying data validation tasks, is it also possible that we risk having biased predictions or false negative, false positive predictions? And there are always these ethical issues when we involve artificial intelligence. So it's very important to see all these benefits, risks, to investigate all these elements before actually involving, combining these two fields, according to me. So thank you so much. I don't know if I have 1 minute more to show the platform very quick, or my time is over.
I believe, Mariam, that it's better to wait later because we are a bit late. So I suggest to go to the presentation of Chris, then to the discussion, and then if it's possible, at the very end, you will show the application.
Okay. Sure.
Thank you. Thank you so much. And on the opposite, as we are a bit late, I will introduce very quickly the last speaker. The last speaker is from the private sector, but is also part of the community of OpenStreetMap. So the last speaker is Christopher Beto, who is a geospatial analyst in the map building team at the Facebook Reality Labs, where his work focuses on mapillary, OpenStreetMap, and building maps using computer vision derived data from user images. His previous work focused on mapillary community, advising practical real-world applications of mapillary data and managing mapillary plugins for the OpenStreetMap and the ArcGIS. Christopher earned a master's degree in GIS from the University of Washington and earned a bachelor's degree at the Santa Clara University in both political science and Middle Eastern studies. He currently lives outside Zurich, so in Europe, and is an active contributor to OpenStreetMap wherever he likes or travels. And so now the floor is yours, Chris. What is interesting is that all of us, we are very close to each other. So Switzerland or Italy, the speakers and me, we are very close to each other. Okay, so the floor is yours.
Thank you. So let's see, make sure that's showing up okay. Is that all right, Maria?
Yes, it's
Great.
okay.
Okay, so yeah, I'm going to talk to you with a quick overview of what mapillary is and how it works. And you'll see some similar themes in how it's related very much to user-contributed images and machine learning in order to derive some meaning from that. In this case, in order to build really any detail of a map. So in one word, or one phrase, we would say mapillary is a collaborative platform for street level images. So the street level side, of course, means it comes from mobile phone cameras, a GoPro, or anything up to the devices you see on top of a car, similar to what Google or Apple might do. But it's also collaborative, meaning it's a user community. So the community is often working together to create images across the entire globe, rather than just working alone on one purpose. So we have 1.65 billion images probably as of yesterday, and we tend to get a few 100,000 at least every day. So it's always growing. Quite a few users across the entire world here, you can see in green. Really a lot of hotspots coming in from Europe, North America, Japan, Australia, and very strong communities in many other places, Southeast Asia, Africa, South America. So it's always growing and changing. And this means a lot of potential for mapping the entire world. So the important thing about the photos that are contributed to mapillary by the users is they are a snapshot of the world at that given point in time. So every photo is geotagged, we know where it is, it has a timestamp, so we know when it is. And then the more technical aspects of it include the pose of the camera. We know which direction it faces, things like how it's tilted, and therefore we can try to actually place where it is in the world, where it is in the local scene, and also build that scene from the photos. So here's just an example of some mapillary imagery that's comparing the same place over time. This was captured by a user on a bicycle in Canada, and their goal was to show the changing infrastructure before and after an improved bicycle safety kind of infrastructure was set up by the city. And the important thing with photos like the ones you just saw is we can actually detect that those are different images. Of course, we can know that the pixels are different, but also semantically classify what's in them as something different. So in this case, what you're seeing is a point cloud, and then the point cloud is changing colors based on the semantic labels of the images. So every user image that's uploaded, the pixels are classified as belonging to some category. So it might be road, it might be sidewalk, it might be building. And these pixels are also used with an open source library. It's called OpenSFM, or Structure from Motion. And what this does is allows using multiple images that are near each other with the geotag close by and with the camera pose and angles known, it's like the compass angle, to reconstruct that scene in 3D. So in a start level, this is not actually geographic information as much as it is just geometric. But one of the important pieces of mapillary is we bring that back into the geographic world. So where you see these sort of lines pointing down to the earth here in the next scene with the icons above, it's indicating the position of specific items recognized in that scene. A trash bin, a water drain, and other things such as streetlights, utility poles, crosswalks. So in a less 3D sense, we can take a look here on the left, for example, another user contributed image. This shows that we detect the kind of entities in that image. So the motorcycle is separate from the car behind it. There's also separate from the two riders that we just classify as a single human entity. And even the building, road, sidewalk, power lines that are crossing the sky above, they all have a different color there, indicating it's a different thing in the image. And you might even see the business sign at the top right. So things like this business sign are dynamic, and we can actually narrow them down roughly to a longitude and latitude, whereas the motorcycle is, or sorry, the business sign is static, whereas the motorcycle is dynamic. So it's going to be kind of removed from the scene in a geographic sense. So on the right side, you'll see, again, we have kind of highlights of these street lamps, traffic sign, and then in that small inset map, we're placing icons showing the location of those items that are extracted from the imagery and placed on the map. So a really quick overview of how this is generated by the user. Again, as I mentioned, a variety of cameras. The best way to get started is with the mobile phone app. So this is accessible to anyone on an iPhone and an Android. But you see in the bottom right also a 360-degree camera made by Garmin, mounted on a selfie stick. And this can be set to capture at 3-second intervals, then uploaded via the desktop uploader application that Mapillary has. So the mobile app looks like this on the top right. Essentially, the focus of Mapillary capture is you hit that red button and it will automatically take a photo every either maybe 3 meters of walking if it has the distance setting on, or you can set it to a timer. So you can set it to be every 1, 2, 3 seconds. And again, it will continue to capture at that interval. And it forms a sequence of images. So the idea is not just a single image, which is the focus of many apps that are involving images and geospatial locations, but instead it's that group of images, often 10, 20, even hundreds, which help reconstruct that scene by having many photos of the same scene from different angles. So the overlap is very important there. And here's an example of some of the other cameras that are relevant. So just keep in mind that this is, it's really any geotagged image is important here. So it goes beyond just the mobile app. And a lot of our focus lately is actually on pedestrian areas. So you'll see someone walking like this, capturing, and it's important because that gives a better view of the sidewalks, whereas the image above on the road is actually focusing much more on capturing traffic signs, anything that's visible with the observer being in a car versus on foot. So that perspective actually helps in determining what type of map data you can generate, especially in an urban area, but really just depends on the medium of travel of that observer. And a last quick example here is looking at the Galapagos Islands. So this is a study we did in cooperation with the University of Chicago, the Mansueto Institute for Innovation. And they had a multi-year program going on where they wanted to map the urbanization in the Galapagos Islands. And they wanted to use Mapillary 360-degree street level images in order to do a snapshot of the port towns in the Galapagos Islands every year. So in the time that I was able to join them there looking at this, we did a very simple analysis that we think maybe will expand in the future. And what happened here is we just divided everything in the image that was detected into the categories of either urban or natural. So vegetation, terrain, and earth were one category, separate from things like roads, buildings, sidewalks, wires, utility poles. And then we just map the density of that in each grid square. So on the bottom left here, you can see the lighter colors are corresponding with the center of the port, and it gets darker going into other areas. Let's see, so it looks like the label is backwards on that, but the urban areas were pretty easily detected by the street level, just like they might be with a ground level view. So there's just another look at the coverage there. So overall, it's really important to think of Mapway as a supplementary tool to other types of tools. Maybe that's satellite image, maybe it's still images that only capture one place or one specific close-up item. And Mapway is more about reconstructing that scene and then turning it into a map of the world. So here's some helpful resources. And of course, please let me know in the questions if I can answer any more details. Thank you.
So thank you, Chris, for your very clear presentation and very nice. So we see also the potentiality of Mapillary and OpenStreetMap together with the machine learning algorithm for extracting pieces of information. So thank you to all our speakers. Thank you also of Aiding being so good of try to stay on time, and then I leave the word to Sidalia for the panel. But before I ask if it is possible to all of you to switch on your camera in such a way that in this part of the panel we can see you. Thank you. So Sidalia, it's your turn now.
Thank you. Thank you for you all that made these very interesting presentations. I have lots of questions here. Let's see if we have, meanwhile, also questions from the public, but maybe I'll try to merge some of them together because we're already a little late. So until what degree do you think the artificial intelligence can replace human intervention? So what is the accuracy of the outputs from artificial intelligence? And also in the presentation made by Miriam and Jens, do citizens actually respond to those questions that are made? So are they intervening as a response, or I don't know if you also made the check, so how many answers did you get or something like that? So maybe we can start by these ones. Maybe Sven, and would you start and then we can go around?
Yes, thanks, Sidalia. With pleasure. So basically, on your question whether AI can or should replace citizen science, I think it's really an important one. And I would even add, do citizen scientists want AI to replace some of their contributions? We had some very, very interesting discussions, especially when it comes to validation, that actually having citizen scientists participating in data validation exercises builds an expertise, and is interesting, and it motivates people to engage with science. So it raises actually rather the opposite question: should AI actually be put in place to really replace what citizen scientists do? So I know this is not really an answer, but for me, it's really all about this complementarity to really find the best match where AI can help us to take over boring tasks we don't want to do or people don't want to do, but also leave exciting questions for people to contribute. I think in future, the most successful approaches will be the wise combination of both. Let me be as brief as this.
Yeah. Miriam, maybe you would like to add some of your experience about this, which actually what you are doing. Well, we are combining the outputs of artificial intelligence with the citizens' contributions.
Yeah, sure. First, I will add one quick point of view that when we are talking about citizen science, I mean, as it comes from its name, from its definition, citizens are the heart of this project. So if combining artificial intelligence and citizen science is going to replace the role of citizens in this project, then I would say that we name it another project, not citizen science, because yes, it's possible that artificial intelligence would replace some task in many projects, but if it's going to happen in citizen science projects, then it actually it's contradictory to the main goal of this project. So this is main thing, and as Sven said, is maybe the goal would be like to kind of ask machines to do maybe some boring tasks or some like simplifying some tasks in this project, but not really replacing humans and citizens in these projects. And to your question, for our application, for the moment, is only one-way feedback, so it's only machine-generated feedback to the participants, and they can get this information and decide if they want to improve their data or not, but they cannot like make a response, which was a good point. I mean, we can think about it for future work, but for the moment it's only a one-way feedback. I don't know if you want to add something.
I maybe want to add something that I also think that the view of artificial intelligence is also changing a little bit. For instance, maybe for 10 years ago, I discovered that my word processor is suggesting autocorrections for the text that I'm doing, that I'm writing. Now, if I'm writing and I make some mistakes, I almost get annoyed that the computer is not, or the tool that I'm using is not as intelligent as detecting these points. So the point is that maybe some years ago, then it was more new, and now people are getting used to it. So I think that also the opinion regarding involving artificial intelligence in different tasks is certainly also changing over time, and it has been different 10 years ago, and it will be different 10 years from now, I think.
Chris, maybe you would like to add something?
Yeah, I think what's really interesting to consider with this type of question is you have crowdsourcing as a very powerful tool and movement of enabling all these applications. And then you also have the machine learning. And it's good to consider where these work together rather than are at odds. So the idea is if the machine learning improves in the output quality, the idea is not that it reduces the need for the number of humans who contribute to a project, but instead it actually increases the impact of each human. So think about, for example, if a machine learning algorithm is generating a map of a city for you. If one human doesn't trust the algorithm so much that they must spend, let's say 1 hour actually examining the outputs, checking the numbers, the angles, it really sinks a lot of time still into validating the results. But if the machine learning algorithm improves, less time is spent on validation. And finally, I think it becomes also a design question. If each human is asked some simple yes or no questions that easily validate the results rather than being presented with just raw data, that design interface can actually make each person really validate more output per hour than ever before. So I think this is the best goal to think of, is making each person be able to accomplish more in 1 hour than they could in the past. And then if you have more people, they can also get much more done together. So it really amplifies it all, I think, looking at that perspective.
Thank you. So, yeah. Maybe Xiang Yong have some question? Okay, if
Wang, do you have questions for our speakers? Wang?
Yeah. And for maybe some questions before, there are 3 questions I have given you. I hope they can answer me the 3 questions. A lot of questions for beta, how to say, B, Chris. Maybe Chris. I found from your maybe PPT slides, there are 65 types of objects, 10 identifications, but there are just 45, another 45 types of objects for map. You understand? And I want to know, how about another 20 types of objects are what things? Sorry?
Yeah, sure. So the other types are things that you like.
If you can show me your slide.
Yeah, sure. Let me bring it back. I think the other types of data generally that we're thinking about there are things that you have difficulty putting on a map by themselves. So some of that is, for example, the sky. We can tell in an image when we have sky, but we don't know exactly where that's going to be on a map. And then the same is also things like the cars, the motorcycles that we don't pinpoint on a longitude and latitude location.
Okay, the 2042, yeah. A lot of questions maybe for you too. Then maybe you can after the slides. I found there are one map for all of the birds. And there are two kind of color, maybe white and green for the imaginary. You mean that I want to know if you mean that the white places low, there is low, almost low imaginary. Maybe you're up to the maybe it's 3 slides or 3 or up to your slides. Could you show your slides? And let me see. Maybe up to maybe the third or fourth slides, your PPT. Sorry, for you?
To us.
Sorry, is the question for us? I didn't.
The question is maybe okay. For your case, for maybe for your let me say stay on the genes, right? And genes. So my question is that for you.
Sorry, Xiao Guang, your question is for Mariam and Ian's.
Yes, a lot of question for Hijin.
Okay.
Yes.
Yeah. Okay.
Okay.
Okay. I want to know if you have given me some example for real-time feedback by the machine. I want to know how about the quality, about the of the real-time feedback by machine.
Real-time feedback.
Yeah.
Okay. So yeah, we can quickly show an example. Yes. Of course. If you can share your screen.
Okay.
Share screen.
Meanwhile, I see that then there is a question from one person, an attendee to Chris. And the question is, can you tell us a good experience of use of mapillary data by a government? And then particularly, I'm interested to understand if there was an application to detect urban road status. So Chris, you can prepare yourself for these questions.
Okay.
So basically, when we have when the user selects a location and the bird species, there is one possibility to get these real-time suggestions based on the location of the user. And then if the user selects the name of the species, they can get the probability of observing that species in that location. So this is the real-time feedback that the user will receive. And about the quality of this, we trained 4 algorithms, and we chose the balanced random forest classification, which gave us the probability mainly over 80% for most of the species. So if this answered your question, if I understood correctly.
And maybe Alata, for these questions, how do you validate the quantity of the real-time feedback by machine?
So how do we validate the quality of the data? Okay.
Yeah.
So, okay. Well, maybe you want to answer, maybe.
Well, we had like this data set which we obtained from eBird data set, which we were already like validated data set from eBird. So we were sure that at least they were expert validated. So these are high quality data. So we used this data set from eBird to validate. So we did cross validation to validate the models that we trained using the eBird data, because they were like the data that we were sure that they were correct because they were validated by experts.
Okay, thank you.
No worries.
So Chris, do you want to answer to the previous question?
Sure.
Yes.
So to Juan's question, it looks like, yeah, the best experiences with government and map-theory data tend to be with traffic signs as the focus. So many cities across the world actually inventory the traffic signs. And that's a very slow process to do with just a field team and survey. So usually they can do quicker with a vehicle and cameras mounted and detecting those and then analyzing them via QGIS, ArcGIS after downloading. But the urban road status, it's usually something more manually done with the imagery. So we have a few different government partners who have taken imagery of motorways or urban roads, and then they will analyze the images manually in order to determine if they have like a quality rating to assign to it or any defects, or compare it to citizen reports who might mention something is wrong in a certain location, so they can quickly view the image corresponding to the location.
May I add an additional question to Sven?
No.
Yeah.
I have no questions.
Sven, in that application you talked about, when you use Facebook or Twitter or Instagram, how do you ask the citizens to geolocate their observations? Are they supposed to add coordinates or just mention a location, or?
Yeah, good question, Sedaya. In fact, because this it relates back to the dependency on different platforms, because originally, indeed, we were embedding a map into a chat on Facebook. This was last year before mid of December. So basically, within the dialogue flow, you could open a map, put your pointer, and we would automatically read the coordinates. However, with the argument of the GDPR implementation, Facebook doesn't allow anymore the opening of maps as a pop-up to collect coordinates. So at the moment we are more and still experimenting and thinking about integration of gazetteer services, so that you basically start entering place names and so on. However, also this is not optimal, because it depends on the level of granularity you want on your locations. And especially if you talk biodiversity outside cities, you quickly arrive at place names at quite, not at the right level of granularity, let's say. So this actually remains to be an issue, how to find an appropriate workaround. But it also shows the dependency on the platforms. If they change the rules, you continuously have to adopt.
Yeah, thank you, yes. Yeah.
Yeah, unfortunately, I believe that it's time for of closing this webinar, even if there are probably other questions. So my suggestion is if you have some questions for the speakers, you can send directly the question to the speaker, or if you want, you can send also to me or to Sidalia Xiaowang. We are collecting them and then sending to the speakers. But again, it was a super interesting webinar, in my opinion. And I want to thank again all the speakers for what they were able of transmitting to us, as a matter of fact. Then I don't know, Sidalia, if you have also to say something, or
just thank you.
Okay.
Just thank you for the interesting presentations. Yes, it was very
Yeah.
interesting discussion.
Yeah, and the good point is that probably we are only at the beginning now, because in the next year we will see much more related to this point of mixing machine learning, so machine and people. And I believe that it will be an interesting story, as a matter of fact. So thank you again to all of you. I see that there are some messages, but I believe it's just for thank you, say thank you to all of you. So thank you again, and see you at the next occasion.
Yeah.
Thank you. Thank you.
Yeah. Bye bye. See you at the next opportunity. Bye bye.
Thanks a lot. Bye bye.